In this video, we're going to calculate cell potentials. For example, we want to know, will a 1 molar solution of iron 3 ions spontaneously react with silver metal? Write the balanced cell reaction and calculate E cell, the cell potential, under standard conditions, which just means that the solutions are 1 molar, it's 25 degrees Celsius, all that good stuff. Okay, so if we kind of want to think of this as an equation, like as a reaction, we've got iron 3 ions, which must have come from something like, I don't know, maybe it was originally something like iron nitrate. Let's use iron nitrate. Where this was iron plus 3, nitrate minus 1. It was a solution, aqueous. And then we're going to add a piece of silver metal. Silver solid. Okay, so think back to first year chem. This kind of looks like a single replacement, where the single element silver would replace the one that's in the compound of like charge. Or like metals replace metals. Silver is normally positive. It's looking to replace the other positive ion. So on the product side, you might have something like silver with nitrate. And then you'd kick out iron. So this would be a solution. And then the iron would be a solid. Singular replacement. And I guess like technically, the silver is usually +1, -1. And then of course we would have to balance it, and that would be a blast. So maybe we'd have like a 3 for the nitrate and a 3 for the silver. There, that looks like first year chem, right? Okay, so now someone had asked earlier, and they said, I remember from first year chem, there was something called a reactivity series. And we had to check it for all single replacements. And we had to make sure that the single element was more reactive than the one it was going to replace. Because sometimes a single replacement would not occur. And they're like, do we have to use that chart? Do we have to memorize the chart? Absolutely not. We're going to use these reduction potentials to figure out if this can work. So you don't have to memorize any kind of like a reactivity list. You won't even be given that on the AP test. We would do something like that in reference to reduction potentials. So here's kind of what they're asking. Will this work? Will this be spontaneous? Which means like, will it go forward? Will I form solid iron? Okay, and again, when they just say that there's like iron 3 ions, it means that they canceled out the spectator. So this was probably like spectator, spectator. So it's just really iron ions reacting with the silver metal. Okay, so let's separate the two half reactions. This is a redox reaction, right? So one of the halves is the iron plus 3 forming iron solid. And remember too, if you mean for something to be an ion in solution, you must put the charge in. And it doesn't matter if you go +3 or 3+, but you have to put the charge in. If you just say Fe, we assume that you're meaning solid iron, which we do want in this case. The other half reaction is the 3 silver forming the 3 silver +1 ions. Okay, so there's my two half reactions, and we should balance the half reactions, right? There's 3 atoms of silver on both sides. There's 1 atom of iron on both sides, or ion. But we also need to balance the charge. So here this would be like +3 electrons, and this would form 3 electrons. We've got to balance the charge by adding electrons. So now I have the balanced half reactions. And then, of course, those electrons would cancel out, and I should get the overall balanced equation. Oxidation involves losing electrons. So this must be my oxidation half. Reduction involves gaining electrons. This must be my reduction half reaction. Okay, so we want to calculate E cell. In order to do that, we need to look up the reduction potentials. So you'll use this chart If you're working in the study guide, it's at the end of your study guide. But on the AP test, they will give you these numbers. You don't have to like dig them off of a giant chart. They're just going to flat out give them to you. They'll be right in the problem. So here I need to find that half reaction. Iron plus 3 and 3 electrons. There she is. Excellent. So there's his reduction potential, negative 0.036. Okay, so I'll write that down. Negative 0.036, and the unit is a volt. All right, now we're going to look up the second one. We want silver forming silver plus 1 ions. But wait a second. This is the oxidation half reaction. That chart's called standard reduction potentials. So we're not going to find that reaction as is listed. We're going to find the opposite. We're going to find the silver ions gaining electrons. But that's okay. We'll look up the reduction potential, and then we're just going to flip it for oxidation. We'll go the opposite of whatever we get for this reduction potential. Okay, so we're looking for silver, silver, silver. Okay, so I find this. Silver plus 1. Whoa. Gaining an electron? 0.8. Okay, so the reduction potential was positive. 0.80 volts. Common question. Well, on that chart, that was 1 silver ion reacting with 1 electron, forming 3 atoms of silver. Since this reaction, 1 atom of silver. Since this reaction has 3 silver ions and 3 electrons, do I have to somehow multiply this by 3? No, no, no. You will never, ever, 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 ever multiply these reduction potentials. It's a very common mistake. I get it. Like, you have to make sure the electron transfer is the same. So sometimes you do have to multiply one of the half reactions. But you do not multiply the reduction potential. The reduction potential is the force pushing the electrons through the system. That force is the same whether you're pushing 1 electron or 3 electrons. So you'll never multiply the reduction potential. However, we do need to make it negative. We do need to take the opposite for reduction or for oxidation. You will always need to do that. When you look up the potentials, you're always going to need to flip 1 for oxidation. Because again, in a redox, there has to have 1 of each. There has to be an oxidation half and a reduction half. You will always flip the oxidation half. But you don't multiply anything. Now, we just add. Oh, well, that's not so bad. So we're going to have negative 0.036 and negative 0.8. So my cell potential, E cell, is negative 0.836 volts. And like again, sometimes I'll put that little degree symbol in. That just means that everything was run at standard conditions. The solution was 1 molar, the temperature was like 25 degrees Celsius. Okay, so here's our cell potential. I'll write the balanced equation. We kind of did that. The cell potential is negative. Will this be spontaneous? No, not spontaneous. No. These redox reactions will only run in a direction that gives you a positive cell potential. So this wouldn't work. If you were a first-year chem kit and you were looking at that reactivity list, this wouldn't work. Silver is less reactive than iron. Here's kind of how we'll use that in AP Chem. We'll use these reduction potentials to predict if a single replacement or a redox reaction can work. They need to run in a direction that gives me a positive cell potential. This will not. However, I could do the opposite. this would be spontaneous. If I had like a solution of silver nitrate or some kind of silver ion, and I added the iron, the solid iron, and I suppose we could balance it because there would be 3 electron transfers. I could form 3 solid silver and the iron plus 3. That would be spontaneous. If I were to have the positive 0.8 and flip the iron, and now make that the oxidation half, positive 0.8 and positive 0.036, that would give me a positive cell potential. So again, that's kind of how we'll do like the whole reactivity thing here. Your redox reactions have to run in a direction that gives you a positive cell potential. If it's negative, it's not spontaneous in the direction given. So that original reaction would be a no reaction.